When I say the words, time might be breaking right now, I do not mean clocks are about to stop or that you will suddenly freeze in place. I mean something more precise and stranger. I mean that the large-scale structure of space-time itself might be evolving toward a state where our usual idea of time stops making sense. To explore that, I need to start with what physics actually says about time, space-time, and the expansion of the universe, and then push those ideas as far as our current theories allow. In modern physics, time is not a separate, absolute river that flows the same way for everyone. In Einstein's relativity, time is one dimension of a four-dimensional structure called spacetime. Events have three space coordinates and one time coordinate. The geometry of spacetime, the way distances and durations are measured, depends on matter, energy, and motion. Gravity is not a force in the old Newtonian sense. It is the curvature of spacetime itself. Massive objects like stars and galaxies tell spacetime how to curve. Curved spacetime tells matter and light how to move. So when I talk about time breaking, I am really talking about spacetime geometry changing in such a dramatic way that our familiar patterns of cause, effect, and duration might fail. To see how that could happen, we need to look at the universe on the largest scales we can observe. On large scales, the universe is expanding. We know this from observations of distant galaxies. Their light is redshifted. The wavelengths are stretched compared to what we would see if they were not moving away. The farther away a galaxy is, on average, the faster it appears to recede from us. This is Hubble's law. It is not that we are at the center of everything. It is that space itself is expanding, and all distant galaxies see roughly the same pattern around them. We measure this expansion with a number called the Hubble constant. It tells us how fast galaxies recede per unit distance. There is a current tension in the measured value, depending on whether we infer it from the early universe, using the cosmic microwave background, or from the late universe, using supernovae and other distance indicators. But regardless of the exact number, the evidence that the universe is expanding is overwhelming. If we run the expansion backwards in time, the universe was hotter and denser in the past. That is the basis of the Big Bang model. The Big Bang is not an explosion into empty space. It is the rapid expansion of space itself from a very dense, hot early state. The cosmic microwave background radiation is the afterglow of that hot early phase, stretched into microwaves by billions of years of expansion. Its pattern of tiny temperature fluctuations encodes information about the contents and geometry of the universe. When cosmologists analyze those fluctuations and combine them with data from galaxy surveys and supernova observations, they find that most of the energy in the universe is not in the form of ordinary matter. The atoms that make up stars, planets, gas, dust, and you and me account for only about 5% of the total energy density. About 25% is in some form of matter that does not emit or absorb light. We call it dark matter. About 70% is in something even more mysterious, which we call dark energy. Dark matter behaves gravitationally like a pressureless fluid. It clumps. It forms halos around galaxies and clusters of galaxies. We infer its presence because galaxies rotate too fast to be held together by visible matter alone, and because gravitational lensing, light bending around massive objects, shows more mass than we can see. Dark matter is also needed to explain the way structure grew in the universe over time. Without it, the tiny fluctuations in the early universe would not have had enough gravity to grow into the galaxies and clusters we see today, given the age of the universe. Dark energy is different. It does not clump on galaxy scales. It appears to be smoothly distributed throughout space. It exerts a kind of negative pressure. In Einstein's equations, that negative pressure leads to repulsive gravity on large scales. Instead of slowing the expansion of the universe, dark energy makes it accelerate. We discovered this in the late 1990s by observing distant Type Ia supernovae, which act as standardizable candles. They were dimmer than expected in a decelerating universe. The simplest explanation is that the expansion has been speeding up for the last few billion years. Mathematically, dark energy can be modeled by a cosmological constant, a fixed energy density of the vacuum itself. That model, called lambda CDM, with lambda for the cosmological constant and CDM for cold dark matter, fits a wide range of data remarkably well. The cosmic microwave background, large-scale structure, baryon acoustic oscillations, supernova, all are broadly consistent with a universe dominated today by dark energy, with dark matter as the next largest component. But we do not know what dark energy actually is. A true cosmological constant would be a property of spacetime, an energy of empty space that does not change in time or space. Quantum field theory predicts vacuum energy, but the naive prediction is far larger than what we infer from cosmology, off by many orders of magnitude. That mismatch is one of the biggest unsolved problems in theoretical physics. There are also models in which dark energy changes slowly over time, sometimes called quintessence, or models where it might interact with other components. At present, observations are consistent with a constant dark energy, but the error bars still allow some variation. Now, what does this have to do with time breaking? In general relativity, the large-scale expansion of the universe is described by solutions to Einstein's equations called Friedmann-Lemaitre-Robertson-Walker, or FLRW, metrics. They assume that on large scales, the universe is homogeneous and isotropic. The scale factor, AT, tells us how distances between co-moving points change with cosmic time t. If AT increases, the universe expands. The dynamics of AIT depend on the energy content, matter, radiation, curvature, and dark energy. In a matter-dominated universe with no dark energy, expansion would slow over time and could either continue forever or eventually reverse into a big crunch, depending on the total density. With a positive cosmological constant, the expansion eventually accelerates and approaches an exponential form. In that case, the universe enters a phase similar to what we call de Sitter space. Distances between unbound objects grow roughly exponentially with time. In a de Sitter-like future, something interesting happens to our notion of cosmic time and our causal horizon. There is a horizon beyond which events can never affect us, no matter how long we wait. Light emitted today from galaxies beyond a certain proper distance will never reach us because space between us and them expands too fast. Over many tens of billions of years, more and more galaxies will cross that horizon. Their light will redshift to undetectable wavelengths. The observable universe will effectively shrink to our local gravitationally bound group. From our point of view, the universe becomes increasingly empty and cold. Star formation declines, existing stars burn out. Black holes slowly evaporate via Hawking radiation over extremely long timescales. Eventually, if dark energy stays constant, space-time approaches a nearly empty, exponentially expanding state. Time, in the sense of change in the large-scale structure, becomes almost featureless. The universe keeps expanding, but nothing much happens on cosmic scales. In that scenario, time does not break. It just stretches on, with less and less structure and activity. But this picture depends crucially on the behavior of dark energy. If dark energy is not constant, the future can look very different. One extreme possibility, still allowed by current data but not favored, is that the energy density of dark energy increases with time. In cosmology, we often describe dark energy with an equation of state parameter W, defined as the ratio of pressure to energy density, W equals P or R. A cosmological constant has W equal -1. If W is less than -1, we call it phantom energy. In many phantom models, the energy density of dark energy grows as the universe expands. If that happens, the expansion accelerates more and more violently. The scale factor can diverge in a finite cosmic time. This leads to what is called a big rip. In a big rip scenario, There is a finite time in the future when the scale factor goes to infinity and the expansion rate becomes infinite. As that final time approaches, structures at different scales are torn apart by the accelerating expansion. First galaxy clusters, then galaxies, then solar systems, then planets, then atoms, and finally even nuclei, depending on the details. The time intervals between these stages can be calculated once you specify the dark energy model. In a strict Big Rip, the future is a finite interval of cosmic time. There is a last moment beyond which the FLRW description breaks down. Time-like in null geodesics, the paths of particles and light cannot be extended beyond that time. In that sense, time as described by that cosmological solution literally ends after a finite duration. That would be a form of time breaking. It is not that local clocks suddenly stop for no reason. It is that the space-time geometry they live in ceases to be extendable. The theory says there is no after in that model. Current observations do not require W to be less than -1. The best fits are close to -1 with uncertainties. Some analyses allow a slight preference for W below -1, others for W above -1, but within error bars. So a Big Rip is not ruled out, but it is not supported strongly either. It is one mathematically possible end state if dark energy evolves in a particular way. Another way time might break is through singularities. In general relativity, a singularity is not just a place where numbers blow up. It is a boundary where geodesics cannot be extended, where the theory no longer gives a meaningful description of spacetime. The Big Bang, when extrapolated back far enough, is such a singularity in classical general relativity. Inside black holes at the center, classical theory predicts singularities as well. Many physicists expect that a correct quantum theory of gravity will resolve these singularities in some way, perhaps replacing them with regions of extreme but finite curvature, or with transitions to other phases of spacetime. But we do not have a complete, experimentally tested theory of quantum gravity yet. In cosmology, there are also models with soft future singularities. These include things like Big Break, sudden singularities, and Big Freeze variants. In some of these, certain derivatives of the scale factor blow up or pressure diverges, while the scale factor and energy density remain finite. In others, the expansion rate tends to 0, but some curvature and variance diverge. The details vary, but the common theme is that the mathematical description of spacetime encounters a breakdown at a finite future time, even if the universe does not end in a dramatic explosion. Whether these are physically realizable depends on the underlying dark energy or modified gravity model. Most of them are speculative and not strongly supported by data, but they illustrate that time breaking in general relativity often means the failure of the geometric description at some boundary. We also need to mention horizons more carefully, because they connect to our sense of time and causality. In an accelerating universe with dark energy, there is a cosmic event horizon. Events beyond that horizon cannot send signals that reach us, even given infinite time. This is similar in some ways to the event horizon of a black hole. For an observer outside a black hole, infalling objects appear to asymptotically approach the horizon, their clocks seeming to slow down. From the point of view of the falling object, it crosses the horizon in finite proper time. The geometry of spacetime means different observers have different accessible regions and different slices of time. In a dark energy-dominated universe, our cosmic event horizon defines the ultimate limit of what we can ever observe. As time goes on, more regions of the universe cross beyond that horizon relative to us. Their future influence on us is cut off. You can think of this as a gradual fragmentation of the universe into causally disconnected patches. Each patch has its own observable history and future. Time within each patch continues, but the global picture becomes more and more fractured. In that sense, the global universal now already does not exist in relativity, and in an accelerating universe, the disconnect between regions becomes permanent. So, could time be breaking right now? On human scales, no. The processes that would lead to a big rip or a far future de Sitter state unfold over billions or trillions of years. Locally, your clock ticks based on local physics. Atomic transitions, oscillations of fields, motion along your world line. Those processes are governed by quantum mechanics and relativity. They are not suddenly altered by the large-scale expansion of the universe in any noticeable way. The expansion of space between galaxies is extremely gentle on the scale of a galaxy or a solar system. Gravitationally bound systems do not expand with the universe. However, from a cosmological perspective, we are living in a special era. We are in the transition period where dark energy has recently become dominant over matter in driving the expansion. For most of the universe's history, matter and radiation controlled the dynamics. In the far future, if dark energy is constant, it will completely dominate. Right now, we are close to the moment when the acceleration takes over the large-scale fate of the universe. In that sense, the long-term structure of cosmic time is being set by dark energy at this epoch. We also have to recognize that our theoretical description might be incomplete. General relativity has passed all tests we can perform in the solar system, in binary pulsars, and in gravitational wave observations. But we have not tested it at the extreme curvatures near singularities, or on the largest cosmological scales with absolute precision. Dark matter and dark energy are, at some level, placeholders for phenomena we do not fully understand. It is possible that a deeper theory of gravity or quantum fields will change our picture of the far future, and even our understanding of what time is. Quantum mechanics adds another layer. In quantum field theory and curved spacetime, the notion of a vacuum depends on the geometry. Particle creation can occur in expanding universes. The event horizon of a de Sitter space has an associated temperature, just like a black hole horizon. An observer in a pure de Sitter universe would see a thermal bath of particles. Over extremely long times, thermal fluctuations might produce rare events, like brief decreases in entropy or even Boltzmann brains, isolated self-aware fluctuations. Whether those are physically meaningful or artifacts of an incomplete theory is debated, but they show that in an eternally accelerating universe, the concept of time tied to entropy and typical states becomes subtle. There is also the question of whether the universe will always be dominated by dark energy. Some models allow dark energy to decay in the future, perhaps converting into matter or radiation or changing sign. In those scenarios, the current acceleration could be a transient phase. The universe might eventually return to matter domination, or even recollapse in a big crunch, leading to a kind of time-symmetric picture where the Big Bang and Big Crunch are two singular boundaries. At present, there is no observational evidence for such a turnover, but the data cannot rule out very long timescale changes in dark energy. Another possibility is that our universe is part of a larger multiverse, with different regions having different values of dark energy. In some inflationary models, quantum fluctuations cause different patches of space-time to inflate at different rates, leading to a self-reproducing multiverse. Our observable universe would be one bubble where inflation ended and reheating produced the hot Big Bang. Other regions might continue inflating or have different physical constants. In such a picture, our cosmic time is local to our bubble. There may not be a single global time parameter that covers the entire multiverse. Time, as a global concept, would then be more like a patchwork of local times. This is speculative and not directly testable at present, but it arises from trying to combine inflationary cosmology with quantum field theory. All of this raises a deeper issue. What do we mean by time breaking? In physics, time is a coordinate in a mathematical model. It orders events and allows us to write down dynamical laws. Those laws, in general relativity and quantum field theory, are local and differential. They tell us how fields and particles evolve from one moment to the next along their world lines. Time breaks when the model no longer provides a well-defined extension of those world lines, or when the geometry itself becomes ill-defined. Singularities, horizons, and phase transitions in the vacuum all represent limits of our current description. Right now, the best data we have suggests that the universe is spatially flat or very close to it, with a cosmological constant like dark energy and cold dark matter. In that model, time does not end in a finite interval. It extends indefinitely into the future, but the universe becomes increasingly empty and dominated by dark energy. The large-scale expansion becomes exponential. Our observable patch shrinks in terms of accessible structures. The cosmic microwave background redshifts to wavelengths larger than the size of our horizon. Eventually, almost all information about the early universe becomes practically inaccessible to any observers that might exist then. From the perspective of those hypothetical or future observers, cosmic history would look very different. They might see only a single galaxy or a small group surrounded by darkness. They might infer a static or slowly evolving universe with no clear evidence of a Big Bang. In that sense, the time when the universe reveals its true large-scale story is now in this cosmological epoch. The information content available to us about the global geometry and history is unusually rich compared to what will be accessible in the deep future. So is time breaking right now? On the scale of human life and human experiments, no. Our local physics is stable and well described by current theories. On cosmological scales, we are in a phase where dark energy has taken control of the expansion. That is not a break, but a transition. It sets the stage for a future where causal horizons and dark energy dominate the structure of time and space. The real break, if there is one, lies at the edges of our theories. We do not know what happens at the Big Bang singularity. We do not know whether dark energy is truly constant, or whether it might evolve into something that causes a big rip, a recollapse, or a phase transition. We do not know how to fully merge quantum mechanics with general relativity in a way that can be tested in cosmology. Until we do, our description of time from the very beginning to the very far future is incomplete. That leaves us with a concrete scientific question. As our measurements of dark energy improve, and as we refine our theories of gravity and quantum fields, will we find that the equation of state of dark energy is exactly -1? Or will we detect even a small deviation that points to a different fate for cosmic time?